Okay, so welcome to this next video, and in this video what we are finally going to do is correlation. We're going to see the concept of correlation. Okay, let me make sure I get this title in view. Yes, there we go. Correlation is the topic for this video, and it's very, very much so related to covariance. So I've shown you how covariance intuitively of two random variables is going to measure how positively or negatively correlated it is. Well, correlation is basically just take covariance and standardize it so that the answer is between 1 and -1, whereas covariance can be between infinity and negative infinity. So that's just the simple idea of correlation, to standardize covariance so that it's you get an answer between -1 and 1. Okay, so the form of the first thing to say is that there are many different measures of correlation. It's kind of like what's that thing in differential geometry, curvature, where there are absolutely tons of different definitions of curvature. There's Riemann curvature, there's Gaussian curvature, and they sort of all overlap in certain ways. But you can define as many curvature tensors as you want. They're all kind of measuring the same thing, and similarly you can define many different forms of correlation. The one we are going to define is the best well known. I was taught this at A level. I think most people are taught it. It's got a great big long fancy name. It's called oh goodness, Pearson's product moment correlation coefficient. Product moment correlation coefficient. I'm sure there's some absolutely brilliant reason that it's called that. Correlation coefficient makes good sense. Pearson's, it probably was discovered by someone called Pearson. Product moment, I don't know where that comes from. Oh, actually, maybe I do. Maybe it's because covariance has a product moment in it. If you remember the definition of covariance of x and y, it's equal to the expected value of x times y minus the expected value of x times the expected value of y. Maybe the product moment refers to this here, that it's got the expected value of x times y, the moment of a product. I don't know. Okay, remember these are the first moments, if you like, and this could be a product moment. Anyway, the correlation, which often is written correlation of x and y, you might often just see it as correlation of x and y, not with the double r, but I prefer the double r. So correlation of x and y, or you might just see it written rho, or r is another symbol that's used to denote it, and it's defined to be equal to the covariance of x and y divided by the standard deviation of x times the standard deviation of y. So that is the definition of correlation of these two random variables. So there, we'll box that up, and basically if we could go back to our example of height and mass, so we have the human population here, 7 billion people, and our experiment is to randomly pick a human, so you can pick one of 7 billion people, and all of them will have a height, so we have a random variable h which is ascribing everyone their height in meters, so let's say this is meters, and we have another one, mass, which is ascribing everyone their mass in kilograms, and those are both random variables, so we're going to let these both be probability spaces in real numbers, and they'll inherit their probability distribution from the probability measure on this abstract probability space. Okay, so we saw how the covariance of h and m were kind of measuring, it was measuring how positively correlated h and m were. So the more positive it was, the more probabilistic it was that that if someone was above the mean in height, they were also going to be above the mean in mass, but if they were below the mean in height, then they'd be below the mean in mass. So those two things kind of went together more than they didn't go together, if this is positive. And basically now what we're going to do is just standardize that, and we're going to divide it by the standard deviation of the height and the standard deviation of the mass. And that basically, the miracle of doing that is that it ensures that this number, the correlation of x and and y, that it's going to be between -1 and 1, basically. And it will give you a -1 if you are very much so negatively correlated, i.e. As height goes up, mass goes down. As height goes above the mean, mass goes below the mean, etc. Or 1 if you are very, very positively correlated, i.e. as height goes above the mean, mass goes above the mean, as height goes below the mean, mass goes below the mean, basically. And I discussed in the covariance video at length some intuition as to why that is true. Okay, why it does give that sort of a measure. Okay, right, so I want to see another way of viewing what the correlation of x and y is, which better shows you why this is going to achieve standardization of this. Okay, so let's turn over. So, another basic, an equivalent definition of the correlation of x and y is that it is just equal to the covariance of, and let's keep to our random variables h and m, because they're nice and intuitive, we know what they are. So covariance of h minus the expected value of h, so I will drop the brackets for expected value because it's just easier, and then we've got the standard deviation of h, again I'll drop the brackets if you please, and then we'll have mass minus the expected value of mass, divided by standard deviation of the mass, okay? So basically what we are doing there is we are standardizing these random variables, and if we take the covariance of the standardized random variables, that is in fact going to be equal to the correlation. So let's just remind ourselves firstly of what these standardized random variables are. So again, we have our human population here, so I'll draw a person to remind us of what it is. We have 7 billion people there, 7 billion. There we go, and we have height and mass ascribed to each one of them, so 0 upwards for mass again. Okay, right, so now what I want to discuss is how do you construct this standardized version of height. So basically what I'm going to do is this random variable ascribes to every single person in this sample space, it ascribes a number. It ascribes a positive, your height can't be 0, so it does ascribe a positive real number to every single person on this planet. What we're going to do is we're going to create another function of this. We're going to create another random variable which we could call h bar, the standardized h, and it's going to be a function of the height. So we're going to take your height. So if you're a person, I'm going to take your height, I'm going to subtract off the expected value of your height, So if you're a human, let's say your height is 1.8, the expected value of height, let's say, is about 1.6, then the difference between you, how much you're above the expected value of height, is in this case 0.2. And I'm then going to divide it by the standard deviation of height. Now let's say the standard deviation of height is, I don't know, I'm making up numbers now, let's say it's 0.1 meters. 0.1 meter, i.e. 10 centimeters. So what we're then going to do is take your distance of 20 centimeters, divide it by the standard deviation, which is 10 centimeters, and we will get 2, basically. And what that tells you is, it tells you how many standard deviations you are within the away from the mean. So if you get a positive value, you're above the mean, and you're that many standard deviations above the mean. So in this case 2, you are 2 standard deviations above the mean. If you get a negative value, it means you're below the mean, and say you've got -1, that would mean you are -1 standard deviation of the expected value. So if you were -1, that would, and since the standard deviation is 10 centimeters, that would imply that you were 1.5 meters, i.e. 10 centimeters below the mean. Okay, so that's what we're going to do. We're going to construct this expected value, this standardized random variable h bar, which just ascribes to every person. Rather than ascribing your height, it ascribes you how many standard deviations you are within the expected, the mean value of height on the population. So why would you want to know that? Maybe just for, if you're tall, you might think that's a jolly good thing to know, that you are above the average, and how many standard deviations you are above the average. I don't know why, but the reason we construct these standardized random variables, say h bar, the reason we construct them is that the expected value of them is is equal to 0. So if we take the expected value of h bar, that's going to equal 0. The reason is if we just plug in exactly what the expected value of h bar is, then we just plug in h minus the expected value of h divided by standard deviation of h. Okay, and I'm sort of half going with the brackets, half not. Okay, then what we do is we just apply the linearity properties of the expected value. We pull out the standard deviation of h, that's not important, and then we get the expected value of h minus the expected value of h. Now, intuitively, if you are taking away the expected value, there should be an equal number of people below the mean, and there should be an equal number of people above the mean. If it were not that case, then it wouldn't be the mean. The mean is defined such that it's in the center of the number of people who are below the mean and above the mean. It averages it all out. So, well, no, it doesn't do that. What I've just said implies the wrong thing. It's almost like a center of mass problem. It doesn't mean that the number of people below the mean and the number of people above the mean are the same. That's the median. That's complete and utter rubbish. It means that the distances away from the mean are all average out. So the average value of the average value of the distance away from the mean is in fact equal to 0. And the symbolic way of just seeing that is that by linearity we can split this up into the expected value of h minus the expected value of the expected value of h. But the expected value of h is just a constant, so we're just taking the expected value of a constant, which is just that constant, so that's just equal to the expected value of h. So these two cancel to give us 0, so the expected value is overall equal to 0. And similarly, if you take the variance of h minus the expected value of h over the standard deviation of h, well, if you pull out a constant of variance, it ends up squared, so you get 1 over the standard deviation of h squared, which is just equal to the variance of h. And then if you take the variance of h minus the expected value of h, well, shifting by a constant doesn't alter the variance, so this is just equal to the variance of h. So this variance of h and this cancel, and you just get 1, basically, as the variance. Okay, so that's why we standardize random variables. Now, we're going to see another reason we standardize random variables, because if you think of these as the standardized variables, then if we take the covariance, that's going to be equal to the correlation. So I want to show you why that is so. Okay, so remember, I want to show you why this matches the other definition we have for correlation. Okay, so if we calculate what this covariance is, so if we take this covariance of these two standardized random variables, h minus the expected value of h, divided by the standard deviation of h, and intuitively think of these as telling you how far away, how many standard deviations you are away from the mean. That's what it's telling you. M minus the expected value of m divided by the standard deviation of m. So if we work this out, if we just go to the definition of covariance, and I think the best one to use is the expected value of h minus the expected value of h divided by standard deviation of h, and I think I should write out the formula for covariance, otherwise I think we're going to get a bit lost here. So the covariance of two random variables x and y is just defined to be equal to the expected value of x minus the expected value of x times y minus the expected value of y, and I'm sorry if you can't see that because it's so close to that lampshade. Okay, so there's what we want here. So x is now taken, the place of x is being taken, let me get my pens, that's not what I want. The place of x here is being taken by this. So I need to put in x here, so I put this in as x, and now I need to put in minus the expected value of all of this thing, h minus the expected value of h, divided by the standard deviation of h. But I've just shown you that the expected value of a standardized random variable like that is equal to 0, so I can get rid of that instantly. Similarly, I would get the place of y is being taken by this standardized version of mass, so I plug that in and I get mass minus the expected value of mass divided by the standard deviation of mass, and again what I would get is minus the expected value of m minus the expected value of m, this standardized mass, how many standard deviations you are away from the mean. And we know, of course, as we've just shown, that right, have I got these brackets right? I just want to make sure. Yes, that's fine. I need one more bracket there. What we've shown is that this thing here is just equal to 0, so we'll get rid of that. So what we get is that this is the expected value of h minus the expected value of h, and I'll drop some brackets to make it simpler, divided by, make sure we keep that divided by, the standard deviation of h. So I'll drop the bracket there. So that's this bit here. Minus 0, so that's gone. And then it's multiplied by m minus the expected value of m divided by the standard deviation of m. Okay? Now, because of the linearity properties of the expected value, we can pull out these standard deviations of h and the standard deviation of m, because those are just constants. So we get that this is the expected value of h minus the expected value of h times m minus the expected value of m. Okay, all of that in a bracket like that, all divided by the standard deviation of h times the standard deviation of m, and this thing you will just recognize as the covariance of h and m. Covariance of h and m divided by the standard deviation of h times the standard deviation of m, and that is the way we defined covariance previously. So that is why that is the way we defined correlation previously. So this is just equal, but by our first definition, to the correlation of h and m. So basically what we've seen is that the two definitions of correlation match one another perfectly. Okay, so what you can think of correlation as doing is taking these two original random variables, h and m, standardizing them, and then taking the covariance, which we have seen is a measure of, gives us an intuitive measure of. So let me just construct this other one. M minus the expected value of m divided by standard deviation of m gives us another standardized random variable here, which we'll call m bar. And basically what you can think of this as correlation of h and m as doing is taking h bar and m bar and taking the covariance of those standardized random variables, basically. So, and we've seen how covariance is intuitively going to measure how positively correlated they are. So basically you can think of correlation as the measure of how positively correlated they are, the standardized random variables of h and m are, which is this h bar and m bar. So there we are, that's the definition of correlation. In the next video what we'll do is we'll prove that correlation only takes on values between -1 and 1.